Let's begin with a brief review of complex numbers. There are many ways to write complex numbers. One of the most common that's taught first is rectangular form. You can also write it in polar form, which is more common in electrical engineering. Mathematicians like complex exponential form, and one can also use graphical form, in which we've got a real part and an imaginary part written out. So to give a concrete example, let's say we begin with a complex variable z, common variable name for complex numbers, and in rectangular notation it is composed of 3 real parts and 4 imaginary parts. That could be written in polar notation as 5 at an angle of 53 degrees. It could be written in complex exponential form as 5 times e raised to the j 53 degrees. That's a perfectly valid equation that we'll evaluate on your calculator. Or it could be written graphically as a number that has 3 real parts, 4 imaginary parts, and so that is the plot of z. One could also plot it graphically as a number that has an angle of 53 degrees relative to the positive horizontal axis, and it is 5 units away from the origin. So the graphical method brings together both the rectangular and the polar methods. When working with complex numbers, you'll also often want to take the complex conjugate. We represent that with a small star and asterisk next to the variable name, and that's equal to the same real part but with the opposite amount of the imaginary part. In polar form, that means the magnitude stays the same and the sign of the phase angle is inverted. Complex exponential form should be obvious by now that that's just another way of writing the polar form. And graphically, since the real part stays the same, but we invert the amount of imaginary part, you can also see that taking the complex conjugate is equivalent to rotating a number around the horizontal axis. Euler's identities are a sequence of rules that can be used to work with complex numbers, and they show how the complex exponential form comes from the rectangular form. In particular, there's 3 that you should be aware of. The first is that e raised to the j omega power can be written as cosine, as having a real part and an imaginary part. The real part is cosine of omega, and the imaginary part is sine of omega. If you were to think about what this looks like graphed, it's a little bit difficult because we've got a single real input, omega. We've got a complex output. You could draw that in 3 dimensions. Here's our real part. Here's our imaginary part going into the screen. And there's our omega. That's our independent variable. And if we start off with this omega being 0, you can see the sign of 0 is 0. We're left with a purely real 1. And as we increase omega up to 90 degrees, our imaginary part will increase to 1, and our real part will decrease to 0. So we'll end up going eventually to this point. But as our omega increases, we end up getting this spiral going around and around and around. So it's a thin one-dimensional line embedded in 3-dimensional space. And that's hard to wrap our heads around, so it's much easier instead to look at it as a 2-dimensional graph. We've got the real part, we've got the imaginary part, and if we graph this for omega equals 0, we are right there. And if we graph it, this is omega equals 0. If we graph it for omega equals 90 degrees, we're up here. If we graph it for omega equals 180 degrees, we're over here. 270 degrees, same thing as minus 90, we're over here, and 360 degrees, we're back to here. And what we're seeing here is this graph up here projected down flat onto the real imaginary axis. So this graph in yellow is this equation here, graphed as omega increases between 0, 90 degrees, 180 degrees, 270 degrees, 360 degrees, and so on. The next part of Euler's relationship works in reverse. It says, what is cosine of omega as a function of these complex exponentials? And you can derive that algebraically from the top line. I'll save you the work and say it's this equation. And similarly, sine of omega looks almost the same, except we subtract instead of add. And the denominator, instead of being j, instead of being 2, is j2. So these are the equations. These are Euler's identities. And you will find that we use them a fair amount when studying this chapter.